Right, so that's really a bit small. So okay, so the first exercise, let's do that orally as much as we can. Okay, so I still have to upload the worksheet for the people who are not here. Sorry about this. Okay, so that's done. So let's have a look at that. All right. First exercise. Some very simple, well, more or less simple questions on Fourier trigonometric series. First one, if I give you the function f of x is equal to cosine of 5x, what's its trigonometric series decomposition? It's trivial, meaning the idea is that if you already have a trigonometric function, its Fourier series, its trigonometric series decomposition is going to be exactly the same. Okay? Why do we know that it's true? First of all, you have to get what would be the period of that function. Okay, and then you know what kind of cosines and sines you can use, and if you perform the integration, meaning that you want to compute explicitly the coefficients, then you would get 0, except when the function you're integrating against is the cosine of 5x. Okay, in which case you would have 1, right? But then idea is that if you already get a trigonometric series, a trigonometric function, its series decomposition is just going to be itself. Okay, next one. Use Parseval identity to prove that two continuous 2-pi periodic functions with the same Fourier series coefficients are equal. Okay, so what do we mean here? You get functions that they have some, let's take the complex one, some coefficients. So that its Fourier series is going to look like this. You get another one. Okay. Idea is that what do these equality mean? We've got this theorem, which is Dirichlet theorem, that tells you basically that if your function is in L2 of, here I've written for a 2-pi periodic function, so Fourier series, trigonometric series are only going to be for periodic functions, or for functions defined on a bounded interval which you have periodized in one way or the other, right? So here I've written that for 2-pi periodic. So usually we will write it this way. Let me close it at one side. Okay? If my function is in L2 of functions, of periodic functions on that interval, then we can compute its trigonometric series or its Fourier series. and we will have an exact equality at every point where my function is continuous. And if I have some discontinuity, then it's not going to be an equality, so that would be almost everywhere. At points of discontinuity, you know it's going to take your series takes the value of the average between the two values of your function. Okay? So this equality is almost everywhere. The idea now is that, well, we say our functions are continuous, so this equality is going to take place everywhere, right? And the thing is that if they have the same Fourier series, does it mean that the functions are the same? And of course, if I write it this way, it's obvious, but I want you to use Parseval identity. Okay? What is Parseval identity? Parseval tells you that the L2 norm of your function, the square is going to be the square of the Fourier coefficients. Okay? Right? So that's, if you use the complex series, that's very simply what you get. If you use the trigonometric series in cosines and sines, you get something slightly different depending on the notations and conventions you use. Okay? So the idea is that what we want to prove is that if my function has a 0 coefficients for its Fourier series, does it mean that it's the 0 function? That's another way to rephrase this question. Okay, you understand? But the original question is that I've got two functions with the same Fourier coefficients. Okay, so you compute the coefficients by integrating your function against the e minus I n s. Okay, they have the same values for these coefficients. How can I use Parseval identity to prove that actually it's the same functions? Okay, so it's not. If I write the coefficients, all right, so let's write that C1 and F is going to be the nth Fourier series coefficient of my first function, and C2 and F, so F1 and F2, the Fourier series coefficient for my second function, okay? And the idea is that they are equal to each other, right? What would be the Fourier series coefficient for the difference F1 minus F2? What is going to be the nth Fourier coefficient of the difference of two functions? Yeah.
The nth of the first one minus the nth of the second one?
Yes. Okay, there's no trap here, it's just as simple as that. Which is going to be the one for the first one minus the one for the second one. Right? Why? Just because if you apply the formula, that's just linearity of the integral. Okay, the nth coefficient of my difference would just be given by, well, the integral of the difference of my function. So, well, you know, you've got this formula. So 1 over 2 pi over pi and pi. Okay, so that's, you have the formulas that are all reminded on the back of the worksheet. That's why I went to that today. Okay, so that's the difference, the nth Fourier coefficient for the difference of my functions. So you know that just by applying linearity of the integral, that's just going to be, you can split that integral into the part with F1 and the part with F2, and you just get that it's the nth Fourier series coefficient for F1 minus the nth coefficient Fourier series for F2. Okay? So that if they are both equal to each other, that would be equal to 0. Okay, so the difference would have a zero coefficients for all its Fourier series coefficients. Okay? So now if I use the Parseval identity, what does it give me? It gives me that the norm of f1 minus f2 is equal to what? So yeah, by definition, that would be the integral of the square, the integral on one period of the square of my function. But if I use Parseval identity, 0, okay, because all my Cn's are equal to 0. And what do we know about the norm? When the norm is equal to 0, what does that mean? Norm of something is equal to 0. What does it tell you about that something? It's just, okay, it's as simple as you want it to be. It means that it's 0. Okay, that's the positive definite property, right? If it's always positive and if it's equal to 0, it means that it was 0 to begin with, right? So norm of that is equal to 0. That's just simply equivalent to f1 minus f2 is equal to 0. Well, the 0 function meaning, right? So that f1 is equal to f2. Okay. Okay, next question. Given a continuous function f, so continuous on R, I mean here, that is 2 pi periodic, show that its Fourier series coefficients are all going to go to 0 as n tends to infinity. How do I know that the Fourier series coefficients, they must go to 0 when n goes to infinity? You can use Parseval identity, for instance. Yes?
Because if the sum doesn't go to 0, we cannot make the subtraction of 2 infinites being equal to 0.
Ah, okay. Forget about this. All the questions are unrelated in that exercise, okay? So I'm just considering a function, any function that has that is continuous. Okay, so that's question 3. Let's assume f is continuous, at least C0 on R. Let's say that it's 2 pi periodic. Okay, so does it have a Fourier series expansion? That's maybe the first reasonable question we should ask. Does it have a Fourier series expansion? Okay, for this you have one single answer. It's the Dirichlet's theorem. Okay, that's the only one theorem we saw actually. The other ones were just formulas in that chapter. So Dirichlet's theorem states that if f is in L2 and is periodic, then you have a Fourier series expansion which is going to be equal to the function almost everywhere when it's continuous and to the mean value when it's discontinuous. Right? So, do we have that f is in L2 of periodic functions? Do we have that it's in L2? assumption is f is continuous and spread. Is that in L2 of minus pi pi pair? So yes. Obviously, we want to apply the Dirichlet theorem, so we should work. Why? What does it mean that f is in L2 of this thing? It means that the L2 norm of f is finite. Okay? And the L2 norm that we have given on periodic functions is so 1 over the period. Okay, so if my period is from minus pi to pi, it's going to be 2 pi. Integral on one period, whichever you put that period, of the square of my function. Okay, that's the square of my L2 norm. Right? So when I'm considering periodic functions, it's not going to be an improper integral. Well, it's just going to have finite bounds because I integrate from the period. Okay? So now, knowing that my function is continuous, does that make a finite value? Yes. Okay, obviously, yes. If my function is continuous, it's going to have a maximum and minimum, and so the square is going to have an upper bound, right? So that's going to be smaller than the maximum of the square of my function, which exists and is finite. Okay? This is smaller than some max value, which I know exists because my function is continuous. Right? So that if you take this integral on 2 pi length interval divided by 2 pi, that's just going to be bounded. Okay? That helps to go. Anyway, okay, so if my function is continuous, I know that my L2 norm is going to be fine. So I know that I can apply the Dirichlet theorem. Yes?
I don't understand this part.
Which part?
F square is inferior to max value.
Okay, that's an old theorem that tells you that continuous function on a bounded interval has a maximum value and minimum value. Okay, so I know that this is going to be smaller than the maximum of my square. I know this value exists and it's finite. Otherwise, I wouldn't have continuity. Okay? Right, so I know that this is going to be bounded above by some finite value, and then I just take the integral on a bounded interval divided by 2 pi. That's just going to be a bounded value. Okay, so the idea is that if my function is continuous, then it's going to be in L2 when I'm considering L2 of periodic functions on one period. Okay, so I can apply Dirichlet theorem, right? So I know that my function is going to be equal everywhere because it is continuous to its Fourier series expansion. So if I write it like this, the complex expansion or the trigonometric series expansion. All right? So then what can we deduce? What we wanted to say is then show that the coefficients, they must go to 0 as n tends to infinity. Okay, so let's use again that Parseval identity. Right? I know my Fourier series is exact, right? I know it exists, it's okay, I can compute that, and Parseval identity tells me that what I know is also that the square of the L2 norm of f is given by the sum of the Cn square. How can I deduce that Cn has to go to 0 when n tends to infinity?
So then the n must converge to a finite, also converge to a finite norm. So it must tend to 0.
Something like this. Okay, yeah, I think you have all the pieces together, but we must put them in order. Okay. So, this expansion exists. and f is in L2, and because f is in L2. That means that this part is finite. This we've already stated. Okay? That means, of course, as I've got an equality, that means that this series, the sum of the Cn square, is also finite. What do you remember about infinite series? Necessary condition for convergence. General term has to go to 0. Okay, that's a necessary condition for convergence. Otherwise, you will never have convergence of the series. Okay, if the general term doesn't go to 0, and here even it's a positive, it's the series of positive values. If it doesn't go to 0, there's no way that this infinite sum is going to have a finite value. Okay, so necessary condition Cn tends to 0. Okay, so Cn tends to 0. Otherwise, I would never have that this is a converging series. Okay? All right. So that means if you've understood the principle of those Fourier and trigonometric series, is that we're going to create approximations of functions, better and better approximations, and I'm just going to add smaller and smaller oscillations. Okay, with well, I mean smaller in terms of frequencies, right? And then it's also going to be smaller in terms of amplitude. All right? Question 4 in that exercise is that to prove that we even have something more, not only the coefficients go to 0, but if ever you have class CK instead of just C0, so up to the kth derivative, everything is continuous, then the Cn are going to be of the order, well, small, negligible, small o of 1 over n to the k. Okay, let me do it for you quickly. It's not, I'd rather us spend some time on the calculations afterwards. So what should we consider here? Let's try with C1 first. That means f prime is C0. Okay? That means f prime, and if f is C1 and periodic, what about the derivative? Derivative of a periodic function? Still periodic, okay? Also, all the derivatives will have the same period. You just get the same slope every time you add one period. All right. So f prime also is in L2, and f prime also has a trigonometric series or a Fourier series. People, if you are not interested in that first exercise, you can already come to the next one. Okay, so f prime is C0, so f prime has a Fourier series expansion, all right? What would it be given by its coefficient? Okay, let's assume 2 pi periodicity. So I write again the same formula, 1 over 2 pi. Okay. Find the relation between Cn of f prime and Cn of f. Okay, work on that expression to find a relation with Cn of f. Cn of f would be the same one, but instead of f prime, I would get f. Okay, so how can you relate it? I want something where I will see, I want to extract of this formula something with f of t instead of f prime. Yes. We don't have that many tools. So let's do some integration by parts here. Okay? So write what you get. What's your question? Okay, so integration by parts. Obviously, we want to find f out of the f prime, so that would be using my usual notation. V prime would be f prime, and p would be f. And so that u is my exponential, and v prime is minus I n times e minus I n t. Okay, so if I write the integration by parts on that, I get 1 over 2 pi. In my brackets, my two primitive functions, so f of t times e minus I n t from negative pi to pi, minus, with a minus here, that's going to simplify, plus I n times the integral between negative pi and pi, f of t, e minus I n t dt. Great. And I've got the 1 over 2 pi. That is also factor. Okay, so here I've got exactly what I wanted. This part is I n times the nth Fourier coefficient of f. Okay? What about the value of this part? So, in pi, I'm negative pi, and I said my function is continuous and 2 pi periodic.
So f minus pi equals pi.
Yes? So the value of f at pi and in negative pi, they're going to be the same. Similarly for the exponential. So that thing is 0. That's cancelling. Okay, so I've got this relation that Cn f prime is In times Cn of f. Or if I write it the other way around, 1 over In Cn of f prime is equal to Cn of f. Yep. It's equal to 0 because f is periodic, periodic to pi, and continuous. That means the value in negative pi and the value in pi of f is the same one. Okay, and same thing for the exponential. Okay, so this is the relation that I get. So what can we conclude from that? We can conclude that Cn of f prime, I know it's it's going to go to 0 as n tends to infinity because that's what Fourier coefficients do. That's the previous question on the side. As n tends to infinity, the Fourier coefficients, they tend to 0. Okay, so this one already tends to 0, and I even divide it by 1 over n. Okay, so this one is small o of 1 over n. Because this one is finite and tends to 0 as n tends to infinity. Okay, that's what we said. Fourier coefficients of any function, right, of any kind of any function that has a Fourier expansion of any L2 periodic function, it has to go to 0. Okay, that was the previous question. We used Parseval for that. That's what we proved. Okay, so this one goes to 0, and this one goes to 0, but I can even divide that limit by n. So that means that, well, we just got that is small o of 1 over n. If it's one time differentiable, then my coefficient is at least small o of 1 over n. Okay, and then you can iterate on that reasoning. If it's 2 times differentiable, you're going to get that it's what, small o of 1 over n squared by applying the same reasoning to the derivative. Okay? And so on. Yes? Here? I times n. What I used was, well, I got this way. I got it that way. Yes?
I didn't really understand when you said the 2 times derivative will be equal to O 1 over n.
Okay, right. So let me. The question is, if f is ck, show that Cn is O of 1 over n to the k. Right? What we proved is that if n is C1, if f is C1, we showed that f is C1, then its Fourier series was small o of 1 over n. Okay? So if f is C2, what does that mean? It means that f prime is C1. See what I'm going to? So that means that Cn of f prime is small o of 1 over n. Okay? What we obtained here was Cn of f was Cn of f prime divided by 1 over n. So from this quality, we also get that then Cn of f is small o of 1 over n squared. Okay? Because we had that it's equal to Cn of f prime divided by In.
And we don't take into account the I.
Well, the I is just a value. Okay? So if you look in terms of modulus, so that the I is just 1. Okay? So that's equal to small o of 1 over n squared if that top one is small o of 1 over n. Okay? Okay, so the smoother the function, the more it goes to 0. Well, I mean it's Fourier oscillation. Fourier series coefficients go to 0. That means the smaller oscillation we have to add of all going to 0. Okay? All right. Number 5. That was actually one of the questions of the Socrative quiz we had at the end of the class. And it's just an application of Dirichlet's theorem. So we had this function that is -1 and 1. So -1 on 0, minus pi 0 and 1. And 1 on 0 pi. Okay. What's the question again? Extended by periodicity. What is the regularity of this function? So it's not continuous, obviously, but we can say that it's continuous and it's even of class C infinite out of the points of discontinuity, which just happen to be for each period, the both ends and the middle point. Okay? So what's the convergence of its Fourier series? Dirichlet theorem tells you it's going to converge everywhere it's continuous to the value. So the Fourier series of that function is going to be 1 if x is between -pi and 0, or x is in 0 pi, and what else? The value at the discontinuities, it's just going to be the mean value, okay, on both sides of the discontinuity. So the mean value here is 0. If I extend my function by periodicity, mean value here is again going to be 0, and mean value here is going to be 0. Okay? So I can say that my Fourier series expansion would be 0 for x is equal to anything times pi. Okay, and k is it. Okay? But that's just a very direct application. Okay, so by the way, we're going to do exercise 3, which is exactly finding the Fourier series or the trigonometric series of this function. Okay, exercise 2, that was one of the videos. So let's do exercise 3. Find the trigonometric series of this function. So if I say trigonometric series, I mean something with cosines and sines or sines. And if I mean Fourier, usually I will try to be precise and ask you for the complex expansion if I want the exponentials. All right, but all these are called Fourier series. What's your question? It stands for the Fourier series expansion.
Okay, let's pretend we're
Related to that function. Yeah? Yes? Oh, sorry, yes. -1. Yes, thank you, thank you. It's the contrary. That's better. Yeah. Yes?
Can you repeat the mean value thing?
Okay. So that's an example, but it's tricky because it's 0. So don't think it's always 0. Let's say I've got my function. Let's say my function is defined on 0L, on 0T. And I want to find some expansion for that. So listen, because it's going to be useful afterwards. And I want to find some expansion for that. You remember, it's not a periodic function per se. It's just a function defined on a bounded interval. So if I want to find a Fourier expansion, I need to periodize this function. All right? And I have many ways to do that. One way is just to replicate that on every period. Okay? And other ways would be to use some odd or even parity. Okay? So let's say I'm going to use some odd parity. No, but that's again going to be 0. Okay. So let's say I've expanded that by odd parity. All right? And that's it. And then I periodize. Out of this, I can do some Fourier series expansion on that. All right. What the theorem says is that the Fourier series is going to converge to the value of my function, so especially here at every point of continuity. But at discontinuity points, it's going to take the mean value. Okay, so in that case, it's still going to be 0, so that's positive. But if ever you've got just a function that is discontinuous, okay, it happens to be discontinuous, and then you have it's going to be you can do its expansion by even parity, for instance. That's going to be the one. The Fourier series expansion is going to converge every time it's got continuity to the same value. And at the point of discontinuity here, it's going to take the mean value of the two. Okay, that's all. Very clear. Yes?
So the horizontal is f on the graph is f, and on the vertical is s of f. The question is the axis, the horizontal one is f.
The axis,
Yes.
x, y.
But why do we have a s of f on the top in yellow, and now we have x and y?
That's a formula for my Fourier series. That's a sketch of what it looks like, the function. Okay, these are separate parts. That's not part of my sketch. Okay? Okay. So let's do exercise 3. I said we have this one. And I want a trigonometric series, so the one with the cosines and sines. So who wants to do this one? Okay, so you have all the formulas that are reminded on the other side. Okay, there is something you have to pay attention when you are using the formula. They are given, assumption is f is in L2 of negative pi periodized. Periodic. Okay, what is the period of f? 2 pi. If I say negative tt, what is the period of it? Thank you. Okay, that means if we want the trigonometric series, meaning the one with the cosines and sines, if you want to compute an, right, what you divide by is half a period. Okay, integrate on a period. That, by the way, there's an L and it should be a T. Okay, okay, in the formulas. So that's a capital T. You integrate on a full period, but you divide by half a period, right? Okay, so f of t cosine and pi t over, again, half a period. Okay? All right. So let's apply it to our function here. Our function, it's the easiest one, it's the 2 pi periodic. Okay, and the bn's are going to be the same, but with a sinus instead of a cosine. So first of all, my function here, can I find a way to not compute half of the coefficients? Yes. Yes, it's an odd function. So what do we know about odd functions? The other one, okay? It's only going to be made out of odd functions. Okay, the odd ones are given by the sinus. All right, so my function f is odd, only sinus terms. Okay, you can still try to compute the cosines, the an, but you will get 0. Okay, if you did your calculations correctly, you would get 0. Okay, then we just have to write the corresponding formula. We only have the Bn coefficients to compute. Yes?
Can you just remind us, please, how do we know it's odd or even?
Depending on the symmetricity you have. Okay? Right. Visually, even functions are going to be the ones that are symmetric with respect to the y-axis. Okay? That's even. Odd functions are the ones that are going to be symmetric with respect to the 0. Alright? But what if you don't have any idea of what it looks like? Odd functions, f is odd, it means f of negative x is minus f of x. Okay, and even function, f of negative x is equal to f of x. Okay? So here we only have to compute the Bn coefficients. What? Sorry? Then you have to compute both. If it doesn't have any kind of parity, you have to compute both An and Bn. Yeah. Sure. Yes?
Can a function be periodic without being even nor odd?
Absolutely, yes. This would be a periodic function without any kind of parity.
And continuous.
Oh yes, of course, yes. It doesn't matter. If I want continuity, I mean that the endpoint and the beginning must be equal to each other. In between, you can do whatever you like. Neither odd nor periodic. That can be a periodic function that is continuous everywhere and has no kind of parity. Okay? So the parity part is just something that tells you, well, I just have half of the coefficients to compute. So who wants to come and do this calculation? I mean, it's one of the easiest. It is? Vincent? Marie? Sorry, can you give me your name? Louison. Yes, Louison. Come on, it's just a matter of writing the formula and then computing that. Yes, listen, thank you.
On the formula, here isn't supposed to be t.
Yes, it's
Oh,
still
okay.
instead of L. Yes, I see that. Okay, yeah, it's T, not L as written in the document. Now it gets better. Okay, so. No? That's why I did it. Okay? So 1/2 a period for this formula. My period is 2 pi, so it's 1/2 pi. Okay, so the 2 pi periodic functions are the easiest one because it's just going to be n times your variables. Okay, whether it's inside of the cosine, the sine of the exponential. Now let's use our function. So it's -1 between -pi and 0 and 1 on 0 pi. No, it's not. It's just now we want to put the real formula for f. Just that it's going to have two expressions, one -1 or 1, depending on the input. No. Adapt this interval.
Yes. But on Bn is going to have a different value.
No. Then we'll have one value. It's that interval that you can split into two parts. One part.
Oh.
Yeah. That's it. Yes? Yes, our function is -1 on that interval and +1 on the other one. Yes?
I don't get why we separate it into.
Because if we now you want to write the exact formula we have for f, it just happens that f is given, well, maybe like this, it's just given as being -1 on -0 and 1 otherwise. Okay, so it's just when we plug the formula for f. Yes. Yes? It should be there. Okay, so we should have some 1/pi in front of everything. Okay, so these are some values you will often have to find. Cosine of n times pi. Okay, think about if n is equal to 1. What is the cosine of pi? -1. Okay? N is equal to 2, cosine of 2 pi. 1. 3 pi. -1. 4 pi, etc. Alright, so the n is going to be -1 if n is odd and +1 if n is even. Okay? Something we can write as -1 to the n. Okay? That's the kind of value you have to be able to use now. Okay? Yep.
So cos of cosinus of Pn isn't equal to minus cos n. No, again,
Cosine is even.
yes.
So cosine of minus, well, if you plug a minus, it's just going to be the same. Okay, so if you have to compute cosine of n pi of minus n pi, it's the same. It's minus 1 to the n. Cosine of n pi, it's the same thing as cosine of minus n pi because that's an even function. So both are going to be minus 1 to the n. Well, of 0, it's yeah. No. Minus 1 power n.
Oh.
Oh yes, you still have to divide by n, but it's just you have to cosine of 0, that's 1 over n minus the cosine of minus n pi, that's minus. Yeah. What is by n? Yes. Let's see. So I guess minus 1 to the n. So I get the same stuff actually. Yeah. Yes. Okay, so we've got Bn. Yes, that's it. Okay, can you write the first terms of that? The few first terms, I don't know, 5 first terms of this expansion here. Okay, so now if I want to write explicitly some terms of this expansion, what are we going to get? So B1, B2, B3, etc. I will just write what you obtain. Okay, so what do we get? So when n is equal to 1, what do we get? Sorry, when n is equal to 1, so that's negative 1. So plus 2, so that's 4 over 1 times 1 over 5. So that's 4 over 5. Okay, so I get 4 over 5 times what comes there. So that's B1. What comes next to the B1? Well, what comes here before calculating the B2?
Exponential of pi.
No, we did the sinus one. Okay, so here the first term is going to be sinus of 1 times x. Okay, next one. B2, what will it be? So that's 2, that's minus 2, that's 0. When n is even, yes, 2 over 2, that's 1, okay, minus 2 times 1. So the n, when n is even, you get that the coefficients are equal to 0. That's what you're going to get. Okay, so let's compute the next one, B3. Okay, so 4/3 pi. Sinus of 3 times x. That's what it tells us for the expansion. Guess what would be the next one? Next one would be 0. We said all the even ones. Next one, non-zero. That would be the one with a sinus of 5x. Yeah, that looks like this. Okay, you have this formula that actually it's this thing is 0 when n is even, and when n is odd, that's going to make 4/n. Okay, so that is my extension. Thanks. What does it tell me? And I think this is one of the examples you had in the 3 blue, 1 brown video, and I think it's also one you have on the Wikipedia page. What does it mean? It means that this expansion gives you better and better approximation of your function using trigonometric functions. That's the idea of the Fourier stuff. So if you want to approximate, the function we want to approximate is that one. The one that is -1 and 1. Okay, and so let's say that this is -5 and this is pi. First approximation we get, and this is 1, is sinus of x times 4/pi. So it's slightly more than 1 4/pi. Okay? So the first approximation we get is actually just something like this. Okay? The best trigonometric approximation I get using just one function is the sinus of x times a bit more than 4/pi. Then I'm going to refine this. I'm going to add things that are, well, a sinus that is oscillating 3 times as fast. So, yeah, but multiplied by 4/3 pi, so it's going to be small oscillations. So I'm going to add something like this. Well, I'm going to add small oscillations, sorry. Small oscillations. There should be 3 periods here. But then, if you add the two together, you see you're getting closer to that straight line. And then you add more and more smaller oscillations, you're going to get smaller, closer and closer when you add them together to my step function. Okay? So you got some animations on that. Or you can try plug this, then this plus that, then the sum of the 3 in any GeoGebra or Wolfram Alpha, whatever. Yes? Which one? Ah. How do we know that? Because that's what is given for us. We know that f is +1 on that interval and -1 on that interval. That's all. I'm using the formula that was given. Probably this, that you have to know. Well, you have to understand and know it. These are some values you know how to compute. Any other questions? That's very smart. Okay, so let's go for exercise, the next one, I guess. 4. Except that I'm not going to ask for a Fourier series. Well, that's something you can do. I want a trigonometric series. Okay, that's an interesting one. Okay. So exercise 4. We want some Fourier series or trigonometric series for f of x is equal to x2 on 0, 2. Okay. Focus, please. So, what can I do with this? I want trigonometric series, not Fourier series, not the complex ones, I mean. What should we do? My function is that one. Define on 0, 2. Okay? What can I do next? So what are you going to compute? Marceau? What should we do? Find the trigonometric series associated to this function. You apply the formula we have, but first, before applying them, we must make that a periodic function. Okay? So it's only defined on 0, 2. So again, we've got 3 ways to periodize. Either we periodize by just replicating on each interval of size 2 my function, or we can use parity to get something slightly simpler to compute. Okay, so if I use an odd parity, what does it look like? So odd parity would be something like this. That's an odd extension of my function. And then you replicate, that makes what would be the period of this function? 4. Okay. And what would the trigonometric expansion look like? Odd, only sinus. Okay? If that's x squared, what is this one? The yellow part. Minus x. Okay. What else can I do? Other kind of extension, but again by parity. So even extension. Extension.
Even extension is maybe better because it's continuous.
Yeah, well, it's also continuous, but it's, yeah, you're absolutely, you're right. That's an even extension. Both are continuous. But this one, what is this formula for x squared? It's the same one. Okay, so I don't have to split into two intervals, it's just going to have the same formula. Okay, so that looks like a good choice. Right? But you could do this one, you could do the other one, you could do whichever. That means you don't have one single trigonometric expansion or Fourier series expansion. You've got many of them. Okay? I could even decide that would be a period 8 function instead of period 4 function. Okay, so let's do this one, the even extension and periodization of my function. So that's going to give me a cosine series. Okay, so work on that, and then somebody is going to come to the board, and I'm going to look very intensely at every one of them. No, you can do either of them.
You can choose.
You can choose, but let's make the even ones. Why is that better? In that case, it's simpler because then your function has the same formula on both sides. Yeah, you get x squared on both sides of the axis. Otherwise, you will have that. Okay, so it's simpler in that case. Yes? These are different forms. You've got the norm and then you've got all the
What is the periodicity?
Okay, so we use the even extension and then we periodize it. Okay, so period again is going to be.
We don't have the A0.
Yes, why not? The A0 goes with the AN.
What is
That is A0. A0, it represents actually the mean value of your function. Or the A0 over 2 represents the mean value of your function.
in the class, say for 2L periodic function, then we have a D. This means that equals 3.
Yes.
Regardez, avant, ce qu'on fait, c'est qu'on avait allé de moins plus à moins. Non, parce que ça, la vie, on a fait de 0. que la période. Non, la période de sera toujours la même. Ça veut dire que là, si je refais le monkey à 0, si je fais le monkey, c'est la même. La période là, c'est de Bitcoin. C'est ça. C'est tout ça. C'est sûr. Ou la période, c'est là où tout est réglé. Et là, c'est tout ce qui est réglé, c'est le pattern. Il fait tout ça.
I apply the formula. I put L square, but it is like a big T square. Because it's big T, so here should be T square.
Yes, yeah, oh, yes. Variable of
Is that
integration?
correct? I'm not sure.
No. It's complete paper. Where is your paper?
I use the
Okay, good old paper, right? A0 goes with the AN, okay? So, 1 over 2, what was that?
4.
Okay, no.
Is that 4?
Yes,
Why not 4?
because function is periodic between negative t and t, that makes 2t periodic. The period is 2t, okay? And so we divide by half a period, all right? So where is that? That's half a period, 1 over 2. Integral between negative t, and I said that between negative 2 and 2 of your function times your cosine, okay? So here we're going to have a 2. Okay, t and y, that's fine. F of t, cosine of t something, dt. That means that we have expressed our integral with the variable of integration being t. And in that case, if your function is y is equal to x squared, when you put that into the zero, it's t squared, depending on the integral, the variable of integration. Okay, so for a0, what do you have? If n is equal to 0, the cosine of 0 is 1. So you just have the integral of f of t dt on the period. No, that means you have taken it the wrong way, I guess. Yes. So the idea is that you lose one exponent of the square, well, at each step. Oh, okay? Yes, the one that we're going to differentiate. Okay, so when you have some integration by parts, and okay, we have one more week, then you have the vacations, and then we have the test. Okay? That means for the test, you have the Fourier series. Next week, we're going to do Fourier transform, so all is going to be for the test. You will have some Fourier series to compute. Okay? Most of the simple ones are the ones that we're doing here. So I won't give you a very complicated one, but probably you will have something of the kind. Okay? What do I mean by something of the kind? You would have, well, in our case here, we have some t squared or x squared. Please. That means when you want to compute the coefficients, you're going to have something like, here we've got the cosine of whatever comes inside, depending on your period. You have to do some IBP for that, okay? Because we don't know of any n times t. We don't know of any primitive for this function. So you have to do IBP. IBP, you know, you have to choose one u and one v prime. The thing is that if you use that to do some primitive functions, you're just going to get exponents, and you're going to get some t cubed times some trigonometric, and then t4 times some trigonometric. It's never ending. Whereas if you lose exponents here, that's the right way to go. Lose one exponent, you're going to get t cosine, t times sine. One more time, your t becomes 1 times the cosine. So that's something you can compute. Okay? So every time you've got t to the, no, not n, to something, p being at, I guess, more than 4, but you can try it for more, right? This is where you want to lose exponents. So that's the one you're going to choose for u, and so that u is t to the p, u prime is p minus 1, so that every time you're going to lose exponents, right? That works if you've got a cosine, if you've got a sine, if you've got an exponential. All these integrals are treated by several integration by parts. Okay, and do the right choice. What do you want in the end? You want to get only cosines or sines or exponentials, so you want to lose exponents here. Do you want to come and do it?
So here
Yes,
They're
yes.
all equal to
Yeah, sure.
At the end,
It looks very good. So I think it's yes. Very good. T is equal to 2. So that's the first thing you have to take care of. All right, what's half of your period? Here it's 2, so that the period is 4. Okay, don't hesitate to put everything that you need for the computation. So U prime is T and V is okay, good. Okay, great.
So we can finish this.
Yep. Yeah.
The period is core.
Yep.
So we have 1 over half the period, but
Yep.
then like the cost over T, not over half the T.
No, it's 2 pi over 2t. Actually, what you have in the cost, that's why you only have pi over t. Okay? So let's go for a second IVP and really fine. Okay, so it's not minus, minus comes in front of it. Just that we must not forget that in the end it was 4 and we will have to minus.
I will have it, but it's inside.
Oh, yeah. Okay, so double IPP, do it as many times as you need in order to be able to do it with ease. Okay, try with the cosines, try with the sine, with the exponential. That's the kind of thing you must be able to do quickly. Yep. Okay, so all the terms in sines are going to be equal to 0. Why? Because we've got sinus of n pi. Okay, 2 over 2 minus 2 over 2 is just going to be sinus of n pi or minus n pi. That's 0. Okay, so only non-zero term being that one. Okay, so we had 1 over 2. Okay, just that we got 1 minus, another minus, so we still have minus. Okay. And we even have one more here, no? Coming from this one. I guess. Yes, because we did all the calculations without the minus. Okay, so let's just simplify this, but it's so we've got so how many minus? We've got 1, 2, 3, so that's minus 1. Okay, 4 over 2, 2 pi n, and then we've got pi n also. And then we have 4 times minus 1 to the n, but 2 times. So 8 times minus 1 to the n. Okay, except that I still have there's a minus that's I don't know where it should. Yes, we should. But we should find in the end 16 over pi square n square, which we get times -1 to the n. Okay, so I don't know what we do with the minus signs, so these ones are. Sorry? Where did it come from?
Yeah, it comes from here.
Yes, that's what well, that's what I see, but according to my correction, we shouldn't have minus 16. Okay, let me. So there may be or maybe not a minus here. What I find should be 16 over pi square n square times -1 to the n. And I don't know why we have a minus that is trailing somewhere. Okay, so to check, you can check at home whether we have a plus or a minus in front of that. Okay, let's use this result to find some other expansions. Okay, let's use this result to find some other expansions. So let me write this somewhere. What do we have in the end? After this calculation, we find that our x squared function should be equal on the interval 0, 2 to this thing here. So 16, so the sum. Oh, we forgot something. We forgot to compute A0, so we need the A0 over 2 plus the sum of so 16 over pi square n square times -1 to the n times the cosine of, well, the corresponding cosine, so n pi x over 2. Okay? We still need the A0. So those of you who have computed the A0, what did you get? So the A0, so 1 over 2 should be 1 over 2, the integral from negative 2 to 2 of t squared times cosine of 0, which is 1. Okay, that's why I'm saying that this is actually, it's not exactly, well, that term, when you divide it by 2 again, it's going to be the mean value of the function on your period, of the square of the function on your period. Okay, so what do we get of your function, not the square? So 16 over 6, so 8 over 3, so 4 over 3. Okay? All right, so let's use that to deduce. In the text it's written Fourier series of x3, but we are also going to do the Fourier series of x on that interval. So what I forgot to write here is that this equality stands for x in the interval 0, 2. Okay? I could also even say, well, for x in interval negative 2, 0, because that was just my x squared function. Okay? But not everywhere, because it really corresponds to the periodization of my function. Okay. So this equality is true, at least on that interval. Okay. Let's deduce the trigonometric series for the function f of x is equal to x, and also f of x is equal to x3.
Sorry?
Yep.
How did you find the A0? Just
by applying the formula. It's the same formula, except that the cosine of 0 is 1. Okay, so I've got t is equal to 2, so from negative 2 to 2 of my t square function, and then we've calculated that. Okay? So deduce the trigonometric series for f of x is equal to x, and then we will do for f of x is equal to x3. So what can I do? I've got the 1 for x squared. What can I do to find the 1 for x? Okay, so I've got the trigonometric series for x squared. How can I find the 1 for x? Okay, I'm surprised. In the other group also they got the same idea. Well, I know that x, at least on 0, 2, will be the square root of x. Not true on the other side. But on 0, 2, that's fine. Problem is that if I take the square root of that side, I have the square root of a sum, and what I want is something like a sum of coefficients times some trigonometric functions. Square root of the sum is completely different than the sum of the square roots. We all agree on that. So it won't look like a trigonometric series. Okay, so if I take the square root, equality would be true, but it's not a trigonometric series that I would obtain by taking the square root of that sign. If I divide by x, I will have a0 over x plus something, a series of cosine over x. That's not a trigonometric series because it's not a sum of trigonometric functions. Yes, we can differentiate. that on the two sides. That's something we learned last year. Okay, well, on power series, but anyway. We can differentiate. Okay, if we differentiate, you get 2x on that side. On the other side, well, that goes to 0. And then we just have to differentiate this one. Okay? If I differentiate that one, well, I get 2x on one side, and on the other side, I just get, well, the sum of 16 times negative 1 to the n over pi squared x squared times n pi over 2 with a minus, okay, from the differentiation of the cosine times the sine of n pi x over 2. Okay, so it does simplify a bit. 16 minus 1 to the n plus 1. Well, not 69, I'm going to keep 8. And n pi sinus n pi x over 2. Okay? That would be 2x. And if I want x, I just have to divide by 2, so I'm left with 4. Okay? So that's very close. Well, sorry. So that is that equality is true for x in 0, 2. If you remember in the videos from the lesson, I was computing the Fourier series, the trigonometric series for the y is equal to x function. Except that we were considering that on period 1 and not on something that has had a different period than that one. I don't remember which period it was. Okay, so that we had a slightly different expansion because it wasn't considered on the same period. Maximilian? Yes? What are you talking about? Okay, so you are checking the result for the previous, so what did you get? Okay, I didn't, okay. So now what can we do? So that's for the x on that interval. So keep in mind that we can have different kind of expansions depending on the periodicity we have applied to our function. Okay, and even depending on if so that seems to hold. I've got only sinus functions, so that seems to hold also on the negative part. Okay, because the previous one was actually true for the x2, also on from negative 2 to 0 and 0. Okay. What should I do to get, yeah? Oh, because I had a minus coming from the integration of, and no, I do it again. I'd rather have this one. No, sorry, I was integrating my cosine, which gives me a plus sign. So not n plus 1, just n. Thank you. Okay, so now, well, how can I deduce the trigonometric series for x3? So we integrate. Okay, so we want to integrate the two sides of this one. Okay, so let me rewrite that. So we want to integrate x2 on one side. So what relation with x3? That would give me, well, 1 over 3 x3. Okay. And on the other side, I want to integrate the whole stuff. Okay. So I've got primitive of a0 over 2. Okay. And then I've got the primitive of that. Of 16 divided 1 CDN over y square n square. So, Vincent, tell me, what can I do with this? I want to integrate that series. Can we do it? Yes, but we have to justify. How should we justify? What do I want to justify? I want to be able to write that it's the sum of the series of the integral. Okay, so does it remind you of something? And what? Yes, some of them. That's Lebesgue, dominated convergence, or Beccoli, or whatever. Okay, that's one of the theorems of the previous chapter that allow you to do that. Okay, how should we do that? That's good because in that exercise we've got many things related to previous chapter and this new chapter. Okay, so how do we proceed for this? We write the partial sums. Okay, we write the partial sums, so that's the sum that stops at capital F. Okay, at a finite bound, right, of the same stuff. Okay, and what we want, we have that this partial sum converges to this, and I want to be able to do that, that the limit of the integral is the integral of the limit. Okay, so we need to find a dominating function. We need to find a dominating function for the partial sum. What dominating function can I get for this? Again, Vincent, Marie, focus on that, please. This way when I see this. Okay, so what dominating function can I ask for? I want something that is going to converge. Yeah. This is 1 over 1. And that leaves me with a series of the kind of 1 over n squared. Okay, so that would leave me with something that is converging. Okay, if my interval is between some finite bounds. Right? So, assuming that we can apply this theorem, and we can because we have found the dominating function, that was just a side note, we can write that we can just integrate term by term, and what do we have? So we get 16 minus 1 n pi square n square. We integrate n pi minus n pi x over 2. Okay? Plus a constant of integration. Okay? Allow me 1 minute. Okay? Plus a constant of integration. What is my constant of integration? And that should be equal to 1 over 3 n squared, x cubed. Sorry. What will be my constant of integration? Take some value. Value in 0 should be 0 on that side. Here 2. Okay, I've got a0 times x, so 0, plus some signs in 0, so 0. So k should be equal to 0. Okay? And Why is that not over yet for the formula? Yes? Yeah, apart from this. It's not a trigonometric series because I've got this x, but we can use the one we have found here. Take the two together, you will get a nice trigonometric series. Okay? You substitute the x by the trigonometric series that we have under here. And you can put all of them together in there. Okay? Try to do correctly that exercise and even finish the part. Bye. Sorry?
The final part.
Yeah.